Okay, fine. So the so today we'll be moving on to the next lecture, and this lecture is genetic algorithm. So basically, in the entire course, soft computing, we are going to discuss three different approaches. One is the fuzzy logic, which we have already discussed. The next one will be genetic algorithm. So in the next few lectures, we'll be discussing about genetic algorithms in detail, and then at last we'll be discussing about artificial neural networks, right? So coming to genetic algorithm, so basically genetic algorithms are used to solve optimization problems, right? See, not only genetic algorithms, all the three approaches, whatever we are discussing, like fuzzy logic, genetic algorithm, and neural networks, all these are basically used to solve optimization problems, right? But they cannot be, but here we are going to discuss such problems, such real world problems which cannot be solved using traditional optimization approaches. So probably you might have learned a course on optimization technique, so where you might have learned traditional optimization technique, that is in using mathematics, how can we find the how can you find the optimum value of a problem, right? The optimum value can be either a maximum value or a minimum value, that depends on the type of the problem. For example, if you want to find the cost, then in that case the optimum value will be minimum, that is always we want to reduce the cost. So if you want to go from here to Delhi, there are say 5 different paths are available, but probably you will choose a path which is less in cost. Okay, so here cost in the sense not only money, it can be time. So time also we can call it as cost, right? So in that case we try to find a minimum value, right? Okay, or say for example, there are somebody may run a business in three different approaches. So in that case he has to follow which approach? So in that case he may want to maximize his profit. So if he follows which approach his profit will be maximized, he may choose that approach, right? So generally optimization techniques are used to solve such problems where we want to minimize or maximize the result, right? Okay. But in case of traditional optimization problems, the problem is comparatively less complex. So it can be solved by using traditional optimization approaches. But that is not the case in most of the real world problems. The most of the real world problems are really complex. They are very complex, and they involve so many parameters. Because of these complexity, because of their complex nature, and as they have so many parameters, they cannot be solved in they cannot be solved using traditional optimization techniques. Okay, so in artificial intelligence there is a class of algorithms which is called as evolutionary algorithms. There is a class of algorithms which is called as evolutionary algorithms. So so one such evolutionary algorithm is called as genetic algorithms, right? So there are different types of evolutionary algorithms which we'll be discussing in the next slide. So one of the evolutionary algorithm is called the genetic algorithm, right? So basically genetic algorithm is also an optimization technique, but this is an optimization technique which is used to solve a problem which is really complex in nature, and which cannot be solved by using traditional optimization approaches, right? So this is the brief introduction about genetic algorithm. Okay, so could someone brief what is genetic algorithm and why we are discussing this? Yes. Hmm. Yes, Akila. What type of optimization problem? I mean, why not we use the traditional optimization approach? Okay, so hmm. Yeah, yeah. So So basically most of the real world problems cannot be solved using traditional optimization approaches. Okay, or or even if it is solvable, it may take a lot of time, or it may be computationally very much expensive, right? So this is the reason why we are looking for different class of algorithms. This class of algorithms is called as evolutionary algorithms. So there are many evolutionary algorithms are available. One such algorithm is called as genetic algorithm. So from this lecture onwards, we'll be focusing on genetic algorithm, right? So before that, I'll give a brief introduction to traditional optimization approach. I'll not be going into the details. Okay, just it's an overview. So you have learned optimization techniques, yes or no? Somebody can respond. Have you learned optimization techniques? A course on optimization techniques? Is it in third year? There is no. You don't have any course like optimization techniques. Any in any mathematics course you have learned this. Find the maximization, minimization, solving maximization, minimization problem. No, no. Okay, fine, no issue. So it's not a difficult thing. I will give a brief intro. Okay. So these are the topics we are going to discuss in this lecture. The concept of optimization problem, what is meant by optimization problem, defining an optimization problem, various types of optimization problem, traditional approaches to solve optimization problem, and what are the limitations of traditional approaches. So basically we'll be discussing a brief intro to optimization problem, different types of optimization problem and its limitations. Because of these limitations, we are going for a different type of approach, which is called as evolutionary algorithms. Okay, so basically optimization problem is in any optimization problem you will be expected to find the maximum or the minimum value. Okay, that, as I said, that depends on the type of the problem. For example, if you want to find the distance between two locations, okay, say for example Hyderabad to say Chennai, you want to find the distance. I mean, multiple paths are available. So this is one path, path 1. This is another path, path 2. This is another path, path 3. Then generally we choose the path which is shorter. Okay, or we choose the path which can be reached in short duration. Sometimes this path may be long, but maybe this may be an expressway, so you can travel very quickly. This path may be short, but it may be through different cities and towns, so it may take more time. Okay, so here our objective is to what? Our objective is to reduce the time. So how quickly I will reach the destination. So this is called as minimization problem. So this type of problem, here we want to minimize the value, right? Minimize the result. Okay. Say similarly, say as I said, something else. Say for example, the say for example, a student, how much mark he will get. Okay, there are different strategy for studying. Okay, say this is strategy 1. If he follows strategy 1, so much marks he can get. If he follows strategy 2, so much marks he can get. If he follows strategy 3, so much marks he will get. Here, what will be the objective? The objective is to minimize or maximize. Yes. In the first case, it is to minimize. In the second case, maximize, because we want more marks. So if I follow which strategy, my marks will increase. So it actually depends on the type of the problem. So either we want to minimize or we want to maximize. Okay. So any problem can be represented generally, not all problems, but generally problems can be represented mathematically. Okay. So there is a so that is called as mathematical modeling. So generally in any scientific approaches, first the scientists or engineers, what they will try to do, in the sense they will try to model the problem mathematically. This is the real world problem, and they try to model the problem mathematically, right? So So as long as you can, as long as there is an option to model the problem mathematically, the solution is easier. Okay, because for most of the things the solution will be available in mathematics. So you have to just apply that solution. That's it. Okay. So whatever the problem, we have to first may create a mathematical model. So the real world problem. So you take a real world problem. So this is a real world problem. I'll say it's a some real world problem that, as I said, maybe finding the distance between two locations, or what is the driving time between two locations, or what are the different strategies a student follows, how much marks he will get. All these are real world problem. First transform the real world problem into a mathematical model. Okay. So once you have transformed the real world problem into a mathematical model, then you have to choose whether it is a maximization problem or a minimization problem. So that depends on the type of the problem. In some cases it may be a maximization problem, in some cases it may be a minimization problem, right? So let us assume this is a mathematical model for a problem. Okay, so the mathematical model is given by this function y is equal to f of x. Y is the output and the model is represented as f of x. Okay, right? And here is one example: 2x minus 6y is equal to 11. So this equation can be transformed like this: y is equal to 2x minus 11 by 6. Okay, so we say y as the output. Okay, so that means if you bring this 6 here, it will become 2x minus 11, right? And then y means 2x minus 11 by 6. Okay, but actually this type of problems cannot be solved by using optimization technique. Why means, here see, for an optimization technique there should be a maximum value, and also there should be a whatever you want to find. If you want to find the maximum value, there should be a maximum value. If you want to find a minimum value, there should be a minimum value. Then only the problem can be solved using optimization approaches. So these problem, if you plot a graph for this, okay, so I'll show you. I found a website where a graph can be plotted for a given equation. Okay, so it is what y is equal to 2x minus 11 divided by 6. Okay, so sorry, yeah, if you plot a graph for this, then how it will look like? Let us see. So this is a nice website I saw. So you can use this website to visualize the graph for any equation. Okay. So this is the equation: y is equal to 2x minus 11 divided by 6. See, this is the graph. If you, this equation, this is the graph. You can see here. Is there any maximum or minimum point? This is basically a line. Is there any maximum or minimum point here? Is there any end for this line? Pardon? Is there any end for this line? There is no end. There is no end. So there is no minimum. See, keep on it is going. So depending on your, as x increases, as x decreases, so this is x, as x decreases, y also keep on decrease. As you increase x, y also keep on increase. There is no, what you call, there is no standard minimum or maximum point, right? So this type of problems cannot be solved by using maximization or minimization approach. So basically this is not at all a maximization or a minimization problem. Okay, so that is what this says. So these are really not related to optimization problems, right? So for an optimization problem, there will be some maximum point and there will be some minimum point. Okay, so if you so that means if you draw it as a graph, the graph will be, it may be something like this. This is fine. Okay, this is fine. This is fine. If it is like this, then you can say that this is the maximum point and this is the minimum point. Now, if the objective is to minimize, then we have to find for which value of x you are getting this output. Okay, and if the objective is to find the maximization, then for which value of x you are getting this output. So this is what we need to find, right? So the function should be something like this. That is, there should be a ultimate maximum point, and also there should be an ultimate minimum point. Okay. And also it may include some constraints. So apart from the function, it may also include some constraints. So here is an example, and a question is given. Suppose you are asked to design an optimal pointer, something like a pointing device. Okay, a device we want to make something like this. It looks like a cone, but one end is a pointer. Okay, optimal pointer made of some material with density rho. Its density is rho. Okay, I mean density is thickness. The pointer should be as large as possible. The pointer should be as large as possible. No mechanical breakage and deflection of pointing at end should be. I mean there should not be any mechanical breakage, and the deflection should be negligible. Okay. So the task is to select the best pointer out of many possible pointers. Right. So this is basically, it is like, it is a cone, right? So the volume of the cone formula here it is being used. M is equal to 1 by 3 pi r squared L, this is height, okay, into rho. Rho is the density, the thickness of this material, right? Okay. And it is simplified like this, right? So deflection. So the question says that the deflection should be negligible, okay? The deflection should be negligible. So deflection is given as a function like this, f1 of d. D is the diameter. So this diameter, okay, and L comma rho, and strength is given again as a function of all these three parameters, right? So this can be written. So here we want to do what we want to minimize. We want to minimize. I mean, this point should be as small as possible. Okay, this point should be as small as possible without any breakage and without any deflection. So that's what we want to do. So it is a minimization problem. Okay, and allowable deflection. How much? So the deflection is represented as dou. Dou should be less than or equal to dou th, and strength should be greater than or equal to STH. Okay, and also the D, the diameter should be between these two things, and length also between these two ranges. So let us not go into the detail of this. So what it says in the sense, for any optimization problem there will be a function, okay, and that function should be either minimized or maximized. Apart from this function, it will also have some set of constraints. These constraints also will be represented through some functions. Okay, so this is a function, and here this function, our objective is to minimize. In some other problem, your objective may be to maximize, and also it will include some set of constraints, right? So this is the general overview of any optimization problem. So this is how we define an optimization problem. So optimization problem will be represented through a function, okay, and that function we want to either maximize that function or we want to minimize that function, and it will be represented something like this: yi is equal to f of, these are parameters. So how many parameters will be there, that depends. Okay, so here the function is represented with n parameters, so that depends with the type of the problem, right? So if it is a very small problem, it may have only one parameter, right? Some real world problem may have 10 parameters or 15 parameters. So this is not under our control, but generally this is the equation format. So the function format is represented like this: y is equal to f of the function of all these parameters, right? And subject to certain constraints. So basically this shows the this shows the default or the standard structure of an optimization problem. So any optimization problem will have a function of this form: y is equal to f of x1, x2, so on up to xn. Apart from this function, it will also have some set of constraints. Again, these constraints can also be given through a function. Okay, so again, how many constraints will be there, and constraints will be on how many parameters, all these we don't know. So here we are giving n number of constraints, x1 to xn. Okay, so these constraints may be operating on some constant ci. So it is given as g of xi to xn ropi of ci. This rop represents some relational operation. ROP represents some relation. Say for example, here this is a constraint, right? So this constraint, what it says that d, the diameter should be between d mean and it should be, that is, it should not be less than d mean and it should not be greater than d max. And length should not be less than L mean and it should not be less than greater than L max. So these are what, these less than or equal to, okay, these are what? These are what operators? These are nothing but relational operators, right? So these are, so these constraints will be normally, it will be based on some relational operators. They will be operated by using some relational operators, right? So that is what it says. ROP, in the sense, it is a relational operator. So relational operators means what? What are the relational operators? Could someone say? What are the relational operators? You can also type in the chat. What are the relational operators? In any programming language, which operators are called as relational operators? Yes? What are arithmetic operators? What are the arithmetic operators? Okay, addition, subtraction, multiplication, division, these are the arithmetic operators. So what are the relational operators? Yeah, Rupesh, yeah, so you name the operator, you are telling some, I am not asking where it is used, name the operator. So these are the relational operators, less than, greater than, equal to, okay, whether two values are equal or not. So generally in C or Java we use double equal to, not equal to, all these are relational operators, okay. So basically an optimization problem will be represented using a function, okay, using a function y is equal to f of x1 to xn of that nature, and apart from that it will also use a constraint, and that constraint will be represented again using a function g of x1 x2 up to xn, and this constraint will be normally operated on some constant, and what operation, it will be a relational operator, right? So this is how we define an optimization problem, okay. So could someone say how will you define an optimization problem mathematically? How do you define an optimization problem? There are basically two things we use. What are the two things? Optimization function and constraints. Yes, this constraint will be operated on some constant, and for operating we use which operator? Relational operators, right? Okay, so that is what represented here. So this g of x1 x2 xn is operated on some constant. So that means what? Xi rop, relational operator di. So instead of ci here they are using di. So it can be either di or ci. Basically it's a constant, right? So or we can say it's ci. Why to confuse? Okay. So something will be there. Okay. So this is the generic structure of representing an optimization problem. Right? So these are some of the classical optimization problems. Traveling salesman problem. So a traveling salesman, what do you want to find? You might be aware of this problem. a traveling salesman, so this is the traveling salesman. He want to visit many cities, city 1, city 2, city 3, city 4, like that he want to visit many cities, okay. So he knows the distance between each and every city from his current location. From his current location to this city, what is the distance he know? Similarly, from his current location to all the locations, all the cities, what is the distance he know? And also he know the distance between each city to the other city. Okay. So now the question is, he has to find a path to visit all the cities in the minimal path. Okay. So this is an optimization problem. And here what is our objective? Is it minimization or maximization? Here what is the objective? Is it minimization problem or maximization problem? Minimization problem. Distance should be as less as possible, right? Similarly, knapsack problem, graph coloring problem, job machine assignment problem. Okay. So these many jobs are there, these many machines are available. How will you assign? Okay. Binary search tree constructions. All these comes under optimization problems, right? Some of them are minimization problems and some of them may be maximization problem. Okay. So, so there may be also some optimization functions in which there may not be any constraints at all. Okay. For example, so such problems are called as unconstrained optimization problem. So in the previous definition we have discussed that any optimization problem will be represented using a function y is equal to f of x1 up to xn, and apart from that it will also have a function which represents the constraint, which is nothing but g of x1 to uh, sorry, this is nothing but yeah, this constraint we can call it a c. The constraint c is nothing but g of x1 up to xn, and it operates on some constant ci. Okay, so this is a relational operator. Okay, but there can also be optimization problem without any constraints. Such optimization problems are called as unconstrained optimization problem. That is, they don't have any constraints. Okay, so here is an example. There is a function minimize. See, here we want to minimize y is equal to f of x1 x2, and this is the function x1 minus 5 the whole square plus x2 minus 3 the whole cube. Here there is no constraints. Here you can see g is equal to null. Okay, there is only one constraint, is x1 and x2 should be greater than or equal to 0. Apart from that there is no constraint. So we want to find a minimum point where this function will give the minimum value. And so basically entire optimization problem can be classified into two categories. One is called as unconstrained optimization problem, and the other one is the constrained optimization problem. In case of constrained optimization problem, there will be a function which is to be maximized or minimized, and also there will be some constraints. So here is a constraint. So g of x1 to xi, and this should be greater than or equal to ci, or any relational operators, right? Okay. So basically this is the brief introduction to optimization, right? And also there are other categories of optimization problem, like real valued problem or mixed integer problem. So real valued problem means if all the design variables are bound to be real values. So design variables means parameters. So here we say y is equal to f of x1 x2 up to xn. Okay, so these x1 x2 xn y, all these are parameters. If all these parameters take real values, okay, real values in the sense fractional values, 1.2, 0.3, like that, if they take that type of values, then such an optimization problem is called as real valued problems. Okay, if some of the parameters takes real values and some of the parameters takes integer values, then such problems are called as mixed integer problem. Okay, say for example x1 takes real value, x2 takes integer value. Okay, then it becomes mixed problem, mixed integer programming problem, right? And the another category is linear optimization problem. If the function is of this form, so here this is the mathematical representation of the problem, y is equal to 2x1 plus x2. So this type of function, this is a linear function, there is no it's not a quadratic or exponential function. So this type of solving this type of problems is called as linear optimization problem. Okay, whereas this is non-linear, this is not linear. Okay, because here something comes in the square, so this is not a linear problem, right? Okay, right. So say for example, if I give a problem like this, y is equal to 4x1 plus 5x2, is it linear or non-linear? Yes. This problem is linear or non-linear? It comes in which category? Is this is linear or not linear? Linear. Okay. So if I give something like this, y is equal to 4x1 square plus 5x2 to the power 4, this is of what category? The second one is what category? Yes. Second problem is what category? Is this is linear or non-linear? So yeah, what about others? Others also you can speak out or you can type in the chat. Okay. So these are different way in which the optimization problems can be categorized. Okay. So like you can call it as a linear problem or non-linear problem, or with constraints or without constraints, right? Okay, these are the different ways of categorizing the optimization problems. And there are different traditional techniques available. It's actually huge, the list is huge. There is a separate course in mathematics available for optimization techniques. So based on that, these are the various techniques available to solve optimization problems, right? So broadly it is classified as linear programming method, non-linear programming method, specialized algorithms. Okay, under specialized algorithm you have dynamic programming, branch and bound, greeting method, divide and conquer. Under linear programming, graphical method is there, simplex method. Under non-linear programming, single variable, multi-variable. Again in single variable you have numerical method and analytical method. In numerical method you have elimination method and interpolation method. So basically these are the exhaustive techniques which are available in traditional approaches to solve optimization problems, right? Okay, so fine. So if you see this particular function, see normally this type of problems, so optimization problems means if you plot a graph for that, you will get something like this. Graph is something like this. So here you can see there is a maximum point and there is a minimum point. Okay. So depending on the type of the problem, we have to find either x1 star or x2 star. So if the problem is to find the if the objective is to maximize the output, if the objective is to maximize the output, then we have to find x1 star. That is for which value of x, when x is equal to x1 star, we are getting the maximum output. Okay. If the objective is to minimize the output, then you have to find for which value of x we are getting the minimum output. So when x is equal to x2 star, we are getting the minimum output, right? And the other points which is other than this x1 and x2, these are called as saddle points. Okay, the other points which is other than x1 star and x2 star are called as saddle points. Okay, that is the point at which you are getting the maximum output and the point at which you are getting the minimum output. These 2 points are called as maximum or minimum, and the remaining point are called as saddle point. And inflection, saddle point is also called as inflection point. Saddle point is also called as inflection point. An inflection point is a point that is neither maximum nor minimum. Okay, So here these two are the maximum points. All the remaining points are called as saddle points or inflection point. So there are, as we discussed, there are many methods to solve the optimization problem in traditional approaches. One of the method is called as analytical method. Okay. So in analytical method, what we do in the sense, given a function y is equal to f of x, which is a polynomial of degree m. So degree m in the sense, for example, if you take this function, what is its degree? Y is equal to 4x1 square plus 5x to the power 4. What is its degree? Its degree is 4. Its degree is 4. Degree is nothing but the maximum to the power what it is having. Okay, this is 4x1 square and 5x to the power 4. So the degree of this function is 4. Okay, and what is the degree of this function? What's the degree of this function? x1 square plus 5x2 to the power 3. Okay, so basically these are polynomial functions of different degree. So this is also a polynomial function of degree 1. So degree 1 is called as a linear function. So this is of degree 2, degree 4. Okay, this is of degree 3. Like that anything can be represented using a polynomial function. But as the complexity of the problem increases, the degree will increase. Okay, as the problem complex. So please understand this point. Any real world problem can be represented using a polynomial function. Okay, but the problem is that as the complexity increases, the number of parameters will increase. First point is number of parameters will increase. Second point, the degree also will increase. See this case, there are in this equation, if you see, where is that? Yes, in this equation you see there are only two parameters, x1 and x2, and its degree is only 1. If there is a function like this, y is equal to 2x, this is very simple. Here it's only one parameter and its degree is also 1. But if you see here, it has two parameters and its degree is 4. Similarly, if you take some other function, something like this, y is equal to 2x1, 3x2 square, 4x3 cube, 5x4 to the power 6, so on and so forth. If it is keep on going like this, say 20x 20 to the power of 12. So there are many parameters and its degree is also 12. So now this is called as a complex problem, because here there are many parameters and its degrees keep on increasing, right? Okay, so here how the this slide, what it shows in the sense, how, using analytical approach, how the optimization problems will be generally solved. Okay, so let us assume there is a function of this form, y is equal to f of x is a polynomial function of degree m. Okay, then there are m number of candidate points to be checked for optimum or saddle points. Okay, and what we do in the sense, we take derivative. So this is the initial function, we take derivatives of different level. Say for example, y1 is nothing but you take d by dx of f of x, first level derivative, that is y1. Okay, y2 is nothing but second level derivative, or you can say this is simply f dash of x. F dash of x is nothing but first level derivative. y2, this is not square, y2 is nothing but second level derivative, you take one second derivative, that is called as f2. Okay, so yn means you are taking derivative for n times, so that is called as yn, right? Okay, so suppose yn is the nth derivative of y, so hence y is nothing but f of x. Okay, so to further investigate the nature of the point, we determine nth higher order derivative. Okay, first you take some derivative, so either you take first level derivative Okay, n, if n is 1, that is first level. Okay, if n is 2, that is second level derivative. If n is 3, that is third level derivative, right? So after taking some level of derivative, you have to check that is there any value of x such that x is equal to x star. Is there any value of x such that x is equal to x star for which y is equal to 0? If you found such a value, okay, and if n is an odd number, then it means that there exists an optimum point at x star. It means that there is an optimum point at x star. Okay, if you could not find such n, if you could not find such x star, which would result in 0 for y, yn is nothing but the derivative of y, okay, or nth derivative of y, then all such x stars are called as inflection point. Okay, so inflection point is also called as saddle point. What is the inflection point? In the previous slide we have discussed what is the inflection point or saddle point. What is minimum, exactly, yes. So the points in x which will not produce a maximum output or minimum output are called as inflection point. So this method, what it says in the sense, given a function y is equal to f of x, you take first level derivative and check, after taking first level derivative you check is there any x star such that y1 is equal to 0. If you found such x star, then it means that there is an optimum point exists at x star. Okay, if you could not find, then all those x stars are nothing but saddle points. Okay, so if you could not find, then you have to take the second level derivative y2. So you have to keep on take derivatives until you find a point x star where yn will be 0. Okay, so then only the derivative, then only we'll stop taking derivatives, right? So now we know that for this x star there is an optimal point available. Now we have to find whether that optimal point is a minimum point or a maximum point. Okay, so for that what you have to do in the sense, in order to decide the point x star as minimum or maximum, we have to find next higher order derivative, that is yn plus 1 is equal to f of n plus 1 for x is equal to x star. Okay, and then you check, then you apply x is equal to x star, then you apply x is equal to x star, and you see what is the result you are getting. If the result is positive, then it means that it is a minimum point. If the result is negative, then it means that it is a maximum point. Okay, so this is how briefly the analytical method works. Again, we are not going into the detail of this. So just you understand that given a function y is equal to f of x, we take the derivative of this, that is y1 is equal to f dash of x, and then we check is there any value of x equal to x star such that this will give 0. If such an x is available, then it means that for that x value there is an optimal value available for this function, right? And once you found that, then you can find the maximum point or minimum point by again taking the derivative of this and plugging the appropriate x star value for x, and if the result is positive, then it means that it is a minimum point. If the result is negative, then it means that it is a maximum point. Okay, so let us stop here about the discussion on what you call traditional approaches. Now we'll get into the actual topic. So before that, I would like to say a few things. Say when you plot a graph for a function, if you get a graph like this, say let us assume you are getting a graph like this. Okay, so this is the graph, right? Now there are different things you should know. See, there is a term called local maxima. There is a term called local maxima, and there is a term called local minima, and there is a term called global maxima, then there is something called as global minimum. So considering this graph, if you take this graph, in this graph, this point is nothing, this point is global maxima. Okay, because in this graph, this is the peak point. So the peakest point of the graph is nothing but the global maxima. Okay, and this point is nothing but global minima. This is global minima. That is the smallest point is the global minima, right? Okay. See, what about this point? What you can call out of these four terminologies? Which name you can give? So this is nothing but local maxima. What about this point? This is, what about this point? This is also local maxima, right? All these points are local maxima. Okay, I'll use different color. What about these points? These points are called as what? These points are local minima, right? Okay, so this is this entire thing is called as problem space. This entire thing is called as problem space. That is these are the different outputs your problem is going to give for different inputs. Okay, maybe this is x the input, this is y the output. Okay, so if x is falling somewhere here, then these are the output you are going to get, right? Now our objective is to find what our, if it is a minimization problem, then what is our objective? Our objective is to find what? If the problem is a minimization problem, then what is our objective? What should be our objective? Yes? Yes, Akila, what are you saying? It's not audible. Global minima. We have to find global minima. If it is a maximization problem, then the objective is to find global maxima, right? So it all depends on the type of the problem. Okay, but actually the challenging part is, assume that you are starting with some x value, say some x value here, which is giving some output here. Okay, say you want to find minimum, you want to find the minimum value, so you will keep on slightly increase the x, so this point will come down, and you will reach this point. Okay, you will reach this point. For here you are getting the minimum value. Okay, say here the minimum value for y is what? Say you are getting some 0.1 or 0.2, right? Now say this is, maybe this is x value, say 3. For x value of 3 you are getting 0.1. Now if you increase x, what will happen? Y will increase or decrease? Are you getting my question? Initially you are here, say this point is 2.5. So slowly when you increase x, y is decreasing. So you are increasing, because your objective is to minimize y, and y is getting decreased. So you are increasing x and you are decreasing y. But beyond this point, if you increase x, say when you make x as 4, what will happen to y? Y will increase or it will decrease compared to the previous value? No, not it should. Based on this graph, you tell. See, for x3 it is giving 0.1. When I say x is equal to 4, based on this graph, what will be y value? Will it be less than 0.1 or more than 0.1? More than 0.1. Okay. So that means, because for y, when you say x is 4, you will get y somewhere here, which is nothing but maybe y is 0.3. But now your objective is to what? Decrease. Your objective is to what? Decrease y, right? But now you cannot, because your algorithm may stop. Your algorithm may get stuck in this 3. Because if you increase beyond this, what will happen? Your y is not decreasing, it is increasing. But actually global minima is lying beyond this point. Are you getting? Global minima, say this may be x value of 6. Global minima is lying here. But in between that point, there is a, what you call, there is a plateau. So this region is called as plateau. So it is going down and then it is coming up. So your algorithm cannot, normally the algorithm cannot sense this. Are you getting? Because it's because so this point is called as local minima. So the algorithm may get stuck here, right? So mainly it all depends on from where you are starting. From where you are starting. If your algorithm starts from here, okay, so if you are starting from here, so that is maybe x value is 5. Now you can comfortably reach global minimum, because for 5 this is your y value, maybe this is 0.25. Now when you keep increasing x, y is keep on decreasing, and ultimately at one time you will reach the global minimum, right. So the challenge is, when you start somewhere else, how can we ensure that you will not get stuck in global minima? But it may happen, you may get stuck in global minima. There is no generic solution for this. There is no generic solution to always find the global minima. There are lot of chances that you may get stuck in local minima, right? Is the point is clear? But all these are solutions. See, but it is not that this is not a solution. This is a solution. This is also a solution to the problem, but this is not a better solution as this. This is much better solution. So that is called as global minima, right? But this solution may not be that accurate. But compared to this, it is more accurate, right? Okay. So these are the type of things which we are going to solve using this optimization problem, right? So basically our objective is to find uh, the global minima, but sometimes these problems may get stuck in local minima, or when you want to find global maxima, it may get stuck in local maxima, right? There are also some techniques available to how to make the algorithm move beyond global minima or local maxima. I mean beyond local maxima or local minima. Right? Okay. So with this introduction, let us get into the evolutionary algorithms. So basically, there are uh, there are certain drawbacks with traditional optimization algorithms. That is, these traditional optimization algorithms cannot be applied for most of the real world optimization problems, because most of the real world optimization problems are really complex in nature. They involve more parameters, and if you try to solve using traditional approaches, then it would be computationally very expensive. And these functions generally they tend to be discontinuous objective function. That is, if you draw an graph for these real world problems, they may not be continuous, they may be discontinuous. Okay. And the traditional approaches are not suitable for parallel computing. It cannot be used with parallel computing, right? And also in case of traditional approaches, it cannot handle discrete values. It cannot handle discrete values, and the traditional approaches are not adaptive. Not adaptive in the sense, with respect to the environment, the approaches will not adapt itself, right? In the real world, you may not always expect the environment to always behave in the same way. The environment may behave in a different way. If the environment behaves in a different way, then some of the parameters may change, right? So these changes in the environment are not included in the traditional approaches. So these are some of the drawbacks of why traditional optimization algorithms cannot be applied for most of the real world problems. So because of this, we are going for a different class of algorithms. These algorithms are called as evolutionary algorithms. So again, these evolutionary algorithms can be classified under two categories. There is a set of algorithms which are inspired from biological behaviors. There are a class of algorithms which are inspired from the biological behaviors of human or any species. Okay. And there are a certain class of algorithms which are inspired from the physical behavior of humans or some species, or some physical behavior of some materials or matter, right? Okay. So basically these algorithms are inspired from nature, you can say, right? So there is a class of algorithms which are inspired from genetics and evolution, and these class of algorithms are called as genetic algorithms. And there is a class of algorithms which are inspired from the behavior of ant colony, and these class of algorithms are called as ant colony optimization algorithms. And there is a class of algorithms which are inspired from human nervous system, and these algorithms are called as ANN, artificial neural networks, right? So these are the three evolutionary algorithms which are based on biological behaviors. Similarly, there are algorithms which are inspired based on physical behaviors. Okay. So there is a process called annealing. So there is a process called annealing in chemistry. So there is an algorithm which is inspired from this annealing process is called as simulated annealing, and the algorithm which is inspired from the movement of particles is called as particle swarm optimization algorithms, right? And the algorithms which is inspired based on human learning system, so this algorithm is called as fuzzy logic. So these are the evolutionary algorithms: genetic algorithm, ant colony optimization algorithm, artificial neural networks, simulated annealing, particle swarm optimization, and fuzzy logic. Okay. So we'll be discussing about genetic algorithms in detail. So I'll give a brief overview of all these things. Ant colony optimization means you might have seen like how the ant were moving. If they found food at one place, they all move in some orderly pattern. Okay, but that doesn't mean that there is somebody is giving them command, so they are moving. No, there is some synchronization in their behavior. There is some synchronization in their behavior, and they collect some signals, and there is some interconnectivity between them, and they understand like where more food is available, or where food is available which are easily accessible. Then every ant follows that pattern, right? So that is also an optimization process, right? Because the ants are optimized towards maximum availability of food. Okay, and they all are synchronized. Okay, so how they might be working. So maybe there are different ants at different places initially. Okay, each were searching the food. Okay, and different ant will get different amount of food. Then they may pass some signal, like I am getting this amount of food here, I am getting. So whichever the ant is getting maximum food, then probably everybody will follow that. Okay, so that is called as ant colony optimization. Similarly, artificial neural networks, human brain. So this is inspired from human brain. Human brain contains several neurons, and each neuron stores some information, and actually they behaves like a complex network, right? So when one neuron may activate another neuron, and it follows some pattern, and accordingly we take decisions, right? So the algorithm which is designed, which is inspired based on human nervous system, is called as ANN, artificial neural networks, right? Similarly, there is a process called annealing. So annealing means uh, it is normally used in metallurgy, where some metals are heated. Okay, they are heated to very high temperature, and while heating, they will be heated very fastly. I mean, this process of heating will be done at a rapid speed. Okay, but later they will be allowed to cool down. But this cooling down will be done slowly. The cooling down will be done slowly. Uh, so basically, what happens in the sense, when you heat, the bond between the atoms or elements will be broken. Okay, and each of the element will become like a individual particle which is wandering, right? Again, when you slowly cool down, they once again settle it at different energy level. Okay, so here also we use simulated annealing. In basically we use simulated annealing to move an algorithm out of the local maxima or local minima, right? Say for example, an algorithm is got stuck in local minima, but we want to move it to the local maxima. Sorry, local minima. It got stuck in local minima. We want to move it to global minima. In that case, you can use simulated annealing, because if you visualize simulated and in simulated annealing, what happens? You are going to heat the metal to extremely high temperature. That is, it will become liquid. The metal will become liquid. Okay. So during that process, what happens? All the bonds between the individual elements will be released, and each element will they can move in the space. Okay, and then it will be cooled down slowly. So once they cool down, now the different elements will settle in different energy level. So it is not that all the elements will settle in the same energy level as they were previous. No, they may take different energy level. So this energy level may be better than the previous energy level. Okay, so that is the idea. Say initially there is a metal, assume. Say there are many, there are many uh, elements like E1, E2, E3, so on. Okay, okay. Say each one has some energy level. Say X1, X2, X3, like that. Now when you heat, no, their energy level will be released, and they can freely move in the space. But when you again cool down slowly, gradually, when you cool down, each of this particle E1 may settle in different energy level. Initially E1's energy level may be X1. Now it may settle in different energy level, which is X3. Okay, so it may be possible that this X3 is better than X1, right? So previously, if the algorithm got stuck here, and now because of simulated annealing, if the algorithm moves here, it is better. It is better for us, because from here it can easily move on to global minimum. Okay, so this is what simulated annealing works. Similarly, particle swarm optimization, it is inspired from swarming of particle. So the ant colony optimization is inspired only from ant. This particle swarm optimization is inspired from different species like birds. If you see, sometimes many birds will they form a group and they will fly, and they move from one country to another country. Okay, so there is some synchronization between their movement, but it is not strictly, they are not following any command. It is not that somebody is giving them order, they are moving. There is some unorderedness, but as a whole it will be ordered. Okay, so so that so it's not only moving of, so it is moving, it also includes moving of, and moving of what you call birds. All these comes under this swarm intelligence. So basically it is a collective intelligence. So it is also called as swarm intelligence. It is a collective intelligence. So they all agree on a collective intelligence, and they follow a particular track, right? So the class of algorithms which are inspired from this is called as particle swarm optimization algorithms. And then fuzzy logic. So all these things are comes under evolutionary algorithms. Right. Now let us discuss on genetic algorithm in detail. So genetic algorithm, basically it is modeled based on biological process, genetics and evolution, right? So generally genetic algorithms are used to solve such problems which cannot be defined mathematically. So previously we discussed that the first step to solve any problem is to find the mathematical model. So once you found the mathematical model, then you can solve the problem. But the question is, can you find a mathematical model for all the problems? The answer is no. Okay, there are many complex real world problems for which there exists no mathematical model, right? So that doesn't mean that immediately you should arrive on a conclusion that for this problem there is no mathematical model. No, your first step, see, as an engineer or a scientist, the first step to solve any problem, you are given a problem. Your first step is to find the mathematical model. You should try fully for this. You have to find a mathematical model. I'm saying it as YMM. Okay. So with all your knowledge, with all available mathematics knowledge, you should try to define a mathematical model for that problem. Okay. but still, if you are unable to find a mathematical problem, or you are convinced that there is no mathematical model exists for this problem, then you can go for these kinds of algorithm, like genetic algorithm or fuzzy logic or ant colony optimization. So these algorithms can be used only for such problems for which there is no mathematical model exists. Okay. So genetic algorithms will be used for those problems for which there is no mathematical model exists, or it is very difficult to model it mathematically. Okay. So generally these problems comes under NP-hard problem. Okay. So NP-hard problem means they cannot be solved in polynomial time. So these are problems which cannot be solved in polynomial time, or so far it is not proven that these problems can be solved in polynomial time, and it involves lot of parameters. Okay. So if a problem cannot be written mathematically, and if the problem is NP-hard problem, and if it involves many parameters, then for such problems we can use genetic algorithm. So the concept of genetic algorithm was introduced by Professor John Holland of Michigan University in 1965, and the first article he wrote on genetic algorithm was published in 1975, right? So the basic principles of genetic algorithm is actually based on biological process genetics and evolution. So this genetics was what is genetics? About this this genetics was initially introduced by John Mendel in 1865, and evolution theory was given by Charles Darwin in 1875. Okay. So let us have a brief intro to genetics before getting into genetic algorithm. So genes are nothing but the basic building block of the human bodies, right? The basic building block in human living, the basic building block is cell. Okay. Each cell each cell contains a hereditary information. Each cell contains a hereditary information. This hereditary information is called as gene. So basically gene represents the personality trait or a characteristic of an individual, right? Okay. And these genes are represented through chromosomes. Okay, there will be certain number of chromosomes, and these chromosomes are fixed for different species. For example, in mosquitoes, the number of chromosomes will be 6. In frogs, it will be 26. In human, it is 46. In goldfish, it is 94. Like that, the number of chromosomes are fixed for different species. Okay. And genes can also be called as genetic code. Genes can also be called as genetic code, and that is for a particular species, the unique DNA code. The unique DNA code is called as gene, right? And this unique code varies from individual to individual. It will not be same. Even for one species, the gene code will vary. Okay, that is for every human, the gene code will be different. Okay, there are two humans, H1 and H2. The gene code of H1 will be different from the gene code of H2. The general structure will be same, but if you study the gene code in detail, they will be unique, so that a gene code can be used to uniquely define a particular individual, right? Okay. So in real world reproduction, how it happens in the sense, so here there are two individuals, X and Y. Okay. So the chromosomes will be, the chromosomes of two individuals will be involved, right? That means half of the chromosome will come from X and half of the chromosome will come from Y, and as a result a new offspring will be created, and this new offspring will have it will get half chromosome from one of the parent and another half chromosome from another parent. Okay. So if it is humans, so each human will have a 46 chromosome. So 23 chromosome from one of the parent and another 23 chromosome it will get from another parent, right? Okay. So these parents, or each of the parents, are called as haploid. Each of these parents are called as haploid, and the resultant offspring which is created, which receives chromosomes from each of the parent, is called as diploid. Okay, so each chromosome from both haploids are combined to have half numbers. That is, each haploid will produce will share half of the chromosomes. Right? So this is nothing to with genetic algorithm, but this is the general genetics. Actually, genetic algorithms works based on this, right? So similarly, there is a concept called crossover in genetic algorithm. See, actually, for everything, whatever in genetic algorithm, we have equivalent terminology in for whatever there is in genetics. We have equivalent terminology in genetic algorithm also, right? So so that we are discussing all these things. So there is something called as crossing over. In genetic algorithms, we have also an equivalent terminology called crossover, right? So in genetics, crossing over means there are two chromosomes. So from these two chromosomes, a midpoint. So it not necessarily a midpoint. Some point will be selected in each chromosome. So this point is called as kinetochore. This point is called as kinetochore. So if this is the point, okay, then in the resultant offspring, let me call it as R. The resultant offspring, it may take one part of the chromosome from here, from the first parent, and the second half from the second parent. Okay, so it is something like this. It will take, right. So this is one option. Otherwise, it can take first set of chromosome from this parent and next set of chromosome from this parent, right? Okay, like this, it may take any one of this combination, right? So say so this midpoint, so this task is called as crossover. So this is called as crossover. And now this kinetochore point, it is not that it should be a center point, it can be anywhere. Say for example, if this point is here, if this kinetochore point is here, then we can call, say, this as C1 and this as C2. Then the resultant chromosome can be formed like C1 C2, C1 C2. That is, first part it will come from here and the second part it will come from here. Otherwise, it may take first part from here, let me call this as C3 and this as C4, or it can take like C3 C4, any combination. So this kinetochore point can be anything. Okay, it can be anywhere. So that depends on like what type of offspring you want to create. So this is called as crossover. So this method is called as crossover. Right. So here is a brief introduction to evolution. Information propagation. So when an offspring is created from two parents, what happens? The offspring will get the genetic code of the parents. So you can say that the genetic code of the offspring will be highly resembled to that of the parents, right? That is, maximum it will match to that of the parents, but you cannot say that it will match 100%. Right? The offspring may also have may have some of its unique characteristics, but mostly it will resemble the parent, right? So that is called as information propagation. So the information is propagated from the parent to the offspring, so which we also call it as hereditary, right? Okay, and but that doesn't mean that the offspring will have only the hereditary information of the parent. No, it may also have its own unique characteristics, which is called as diversity. So the variation in characteristics in the next generation, that is called as diversity. Okay, so this variation may occur due to different reasons, right? Due to environment or different reasons, right? Okay, and then there is something called as selection, survival of existence. Only a small percentage of the offspring produced survive to adulthood. So that is called as selection, right? Okay, and survival of the best. Offspring survived depends on their inherited characteristics, will be ranked. So we will rank all the offsprings, okay, and we will identify which offspring is best. So rank means something like estimating the strength of the offsprings, right? So there is something called as mutation to make the process forcibly dynamic when variations in population going to be stable. So see, basically mutation means, as we have discussed, the genetic code. So generally the genetic code is carried from the parent, but apart from this, the environment may also make some impact on the genetic code. So this environmental impact is called as mutation, right? Or this environment, in the sense, it can be either physical, or it can be anything, right? Say for example, if a particular animal is exposed more to sunlight, then its genetic code may vary to some extent. So that process is called as mutation. Or if an or if an a particular animal is exposed more to cold, then its genetic code may vary, right? Okay. So this is in a brief in view about genetics. So we have some set of population. From this, the mating pool were selected, and then new populations will be generated. Okay, offsprings and mating will be done, and then the new population will be generated. So after generating the new population, you estimate the strength of the new population. That is estimating their survival of fitness. Okay. So this is the overall framework of GA, genetic algorithm. So whatever previously we have discussed was about genetics. So how we can relate genetics to genetic algorithm, that's what we are going to discuss. Okay. So here also we use the term population, but actually in genetic algorithm, the population corresponds to a possible solution. Okay. So in genetics, population represents a particular person or a species, or individual in a species, right? But here in genetic algorithm, population represents a possible solution. Okay, possible solution. Now, possible solution. Okay, now we want a better solution. See, everything may be a possible solution, but we want a solution, but we want an optimal solution. But we want an optimal solution. So that is our objective. Okay. So we start, the algorithm starts, and then we have some initial population. Okay. So how this initial population is generated by using some random process. This initial population is generated by using some random process. Okay. Then from this initial population, we randomly choose any one of the individual population. So individual population is nothing but it is a solution. It is one of the solution. Okay. Then you check whether it is converged or not. Converged means what? Converged means, are you happy with the solution? Okay. So converge in the sense, am I happy with the solution? Am I okay with the solution? That is called as converge. Okay. So initially we may not be converged, we may not be happy with the solution because it is a random solution. So if you are not converged, if the solution is not converged, then go to the next step. It is selection. So selection means from this initial population you select any two items or any two individuals. So from this initial population, select any two individual. So I1 and I2. So here individual means what? Select any two possible solution. Select any two possible solution, right? So after selecting any two possible solutions, from this you perform reproduction. That is, perform crossover. So when you perform crossover, you will get a new solution. So individual I1 is one solution, I2 is another solution. From this we are creating a third solution, which is called as I3, right? So this is the new solution. Now you got a new solution. Again you come back and check, are you happy with this I3, this new solution or not? If you are not happy with I3, then once again go for selection. Again you select some other items or some other individual. Individual is a solution in this case. Okay. So maybe I3 and I4, and again perform crossover, create new solution. So again maybe this time it is I5. So this, are you happy with this I5? Is the solution is converged or not? Okay. and if you are happy, then stop the process. If you are not happy, keep on repeating this until it is converged. So this is how the genetic algorithm is going to work, right? So this is the overall structure of the genetic algorithm. So there will be an initial set of population. These here population in the sense each individual is a possible solution. So from this randomly pick up any one solution and check whether it is converged or not. Converging means are you happy with the solution or not. Okay, if you are not happy with the solution, then go for selection. Select any two individuals and then perform crossover and create a new solution and check whether the new solution is converged or not. If it is not converged, again repeat the same process, right? So this is how in broad the genetic algorithm will be working, right? Okay, so could someone summarize this flowchart, how genetic algorithm works? Because this is the overall view. With this understanding only we have to move further. Yes. Hmm. So each I mean each individual in the solution is what? Each individual in the population is called as what? Each individual in the population is called as what? Each individual is a possible solution, right? Each individual is a possible solution. Okay, we select, yeah, from this you have to select and then you have to if it is not converged, then select any two solution and then perform crossover, create a new solution and then check is it converged or not. Okay, right? So converging, how will you do converging? So this is a crucial question. So converging means one is you have to look for global minima or global maxima. That is one point, right? But sometimes your algorithm may never reach global minima. Okay, say your algorithm is not at all going to reach global minima. Then how are you going to stop? So there are converging means there are two things to converge. Okay, first thing is you try for a best solution. So best solution means what? Say you know this is the global minima. Okay, so generally we don't know global minima, but I'm saying just for understanding. So whatever the result you are getting, you are comparing with global minima. If it is not equal to global minima, then you are telling again select, again reproduce, again you check. You are keep on doing this, right? But after several iterations also you are not getting the global minima. Okay, then convergence actually you have to look it in different way also. So you can see this also one option, whether the result is or is nothing but result, whether the result is reaching to global minima, or otherwise you have to also check if the result is equal to previous result. Okay, if the result is equal to previous result means there is no improvement. That is, in the previous round also I got the same output. In this round also if I am getting the same output means there is no improvement. Are you getting? So like that, how many rounds I will allow? You may keep some threshold. Say last 5 rounds or last 10 rounds, there is no improvement. You are getting the same output. Then there is no point in continuing further. So then also you can converge, because this is the best this algorithm can do. Right? So this convergence actually takes in two forms. Either you can keep a threshold value and you can say that until this threshold value is reached, I will keep on do. Or otherwise you can compare the previous output and the current output. If the previous output and the current output were same, then you can stop because the algorithm is not going to improve further. Are you getting? Right? So these are the some of the ways to converge. Or or there is something called as cost. You can evaluate the cost of any function. Sorry, cost, cost. You can evaluate the cost of any function. So what is the cost? So generally ideal case is cost should become 0. Ideal case is the cost of the function should become 0. So after producing the result for this particular individual, when this for this particular individual, whatever the result is produced, what is the cost involved in this? So if the cost is not 0, then you repeat it. Okay. But sometimes you may not reach, you may not be able to reach 0 cost. So in that case also again you have to do like in the previous round, if the cost is say 0.5, in the current round also the cost is 0.5, or in the past 10 rounds the cost is 0.5, there is no change, then also you can stop the algorithm, right? Okay. So could someone say what is convergence? Are you getting what I'm saying? What are the different ways in which you will converge? How this converge happens? Yes. How do you converge? Should I repeat it? See, convergence means either you look for the optimal solution, and you say that until the optimal solution is reached, we won't stop the process, and you keep on iterate it. So that is one way. But sometimes, fine, if you get the optimal solution, it is fine. Sometimes even after repeating for 1000 times or 10,000 times or 1 lakh times, the problem is not converging. Then you have to settle. Okay. Then you can say that in the past several rounds, if the cost is not at all improving, it is same, say for the past 5 or 10 rounds there is no improvement in the cost, then we can stop. That is also one way to converge, right? Okay. So this is the general process how a genetic algorithm works. So genetic algorithm is an iterative process. So here in the previous flowchart you might have seen, it's a keep on repeats, right, until it converges. So it is an iterative process. So basically it is also a searching technique. So we are search in the sense from the initial population, we randomly pick up some individual, then we perform crossover, and then we try to create better individual or better solution. So that it is called as a searching technique. Okay. So working cycle with or without convergence. So either it can work with or without convergence. Okay. So convergence in the sense, yeah. So sometimes you may say that I have to, the algorithm should work until it reaches the optimal solution. In that case there is no convergence. Otherwise you say that the algorithm should work until the last 5 results were same. So that is with convergence. Okay. Solution is not necessarily guaranteed. Usually terminated with an local optima. Are you getting? So local optima. So it is not that the genetic algorithm will always give you a best solution. No, because your problem space is huge. So for these problems, identifying a best solution always not possible. So some matter of luck is also required. Okay. So as we already discussed, if you are starting from here, it is highly likely that you will land up here, which is a local maximum, which is a local minimum. But if you are starting here, then it is highly likely that you will end up here, which is a global minimum, right? So absolute solution is this, but it is not always guaranteed. So usually the algorithm will terminate with a local optima. That doesn't mean that this is not a solution. This is also one of the possible solution, but this solution is not as good as this solution. So this is a detailed framework of genetic algorithm. I'm not sure whether it is visible or not. Okay. So whatever we have discussed in the previous diagram, the same thing here we are discussing, but in a in a more detailed way, right? So we are starting, and then there is an initial population. Okay. So the initial population includes all these things: defining parameters, representing the parameter, creating the population. So here population means population is a collection of individual, and each individual is a possible solution. Okay, each individual is a possible solution. So here individual population means it's a collection of individual, and individuals are nothing but possible solutions in the context of genetic algorithm. So from this population we pick up a random solution, that is random individual, and check whether it is converged or not. If it is not converged, then go for the next step, which is selection. So in selection we select any two individual, okay, and evaluate their fitness, right? So we want individual with good fitness score, okay, and then perform mate. So here mate in the sense it is basically crossover, okay. So it is selecting mate. So whatever the individual you have selected here, for that individual evaluate the fitness, and then select a mate which is another individual, and then perform crossover. So crossover is, as we already discussed, so there will be, you take a minimum point. So this is one chromosome. So here chromosome is nothing but a solution. This is another chromosome. Then identify a point. So if this point is identified, say this we call it as A, this we call it as B. Then we can say this part is A1, this part is A2. Then we can say this part is B1, this part is B2. Then the new offspring can be either A1 B2 or B1 A2. So it can be any combination. It can be A1 B2, that is first part comes from here and second part comes from here, or it can be B1 A2, first part comes from here and second part comes from here, okay. So that is what is called as crossover, right? Okay, I think it's clear. So initially we select one individual, that is one solution, and it is not converged, then evaluate the fitness of this individual, that is individual 1, then select another individual, okay, that is select another solution, perform crossover, okay. So after crossover you will get either A1 B2 or B1 A2. Then perform mutation. Mutation means some changes in this, whatever the offspring generated, we may create some additional changes. In biology, mutation happens due to environment, either due to extreme weather or due to extreme emotional states. Mutation happens, okay. So say for example, two parents a parent may have twins, okay. So there are two, child 1 and child 2, okay. But say that one child was grown up in a country which is extremely cold, and another child was grown up in a normal country, okay. Then this child gene may be little different because of the cold weather, that may affect the gene, okay. That is called as mutation. That process is called as mutation, okay. So here also after crossover we this entire solution, this is the new solution, right, which we call it as new individual or new solution. So this new solution or new individual will go through mutation. So during mutation we may change some of this bit value. So here everything will be bit, zeros and ones. So some information we may change, okay. So then we go for some process called inversion, okay. So this is also, here also we perform some change in the genetic code or this individual's bit value, and after all these things a new individual or a new solution will be created, and then we check whether it converges or not. If it is converged, then stop the algorithm, otherwise again repeat this process, right? Okay. So for any optimization problem, you should identify all these things. What is the objective function? What is the constraints? What is the input parameters? How are we going to evaluate the fitness? That is, how we are going to say that this solution is better than this solution. So that is called as fitness. How are we going to evaluate that? And there is something called as encoding and decoding. Encoding means in the real world we may represent the values in one notation, okay, but genetic algorithm may need this data in a different notation. So then the data should be converted in the form which is understandable by genetic algorithm. So that is called as encoding. Are you getting? Similarly, the genetic algorithm may produce an output in an encoded format, but the real world may need an output in a different format. Then again the output should be converted to the form which is understandable by the real world. That is called as decoding. Okay. So encoding means basically converting the input to a form that will be understandable by the genetic algorithm. So that is called as encoding. Decoding means converting the result produced by the genetic algorithm to the form that will be understandable by the real world. Okay. So all these things are defined here. Encoding means how to represent a solution to fit with GA framework. So here solution means individual. Okay, each in the set of population, each individual is a possible solution. So how to represent that solution in a GA framework, that is called as encoding. Convergence means how to decide the termination condition when the algorithm will terminate. Okay. Mating pool means the how to generate the next solution, the set of individuals selected for crossover, that is called as mating pool. Fitness evaluation, how will you evaluate a solution? Okay. Crossover, how to make the diverse set of next solution. Okay. Mutation, that is to explore other solution. It is how you change after crossover. There may be some changes can be performed. That is called as mutation. So inversion means to move from one optima to another. So that is called as inversion. Say so inversion is nothing but moving from a local optima to some other local optima or to some other global optima. That is called as inversion. Say for example, if the function is something like this, then this local maxima, this local minima is better than this local minima, right? So if you move from this local minima to here, that is better, right? So that can be done by a process called inversion. Okay. So there are different GA strategies exist. So these are called as simple genetic algorithm, steady state genetic algorithm, and messy genetic algorithms. Fine, let us discuss this in the next session. So we can stop here. So in today's lecture we have discussed a brief introduction to genetic algorithm and an introduction to optimization technique and why the traditional optimization techniques cannot be used for most of the real world problems, and because of that we are going for evolutionary techniques like genetic algorithm, fuzzy logic, artificial neural networks, and colony optimization, all these things, right? Fine, let us stop.